AP Physics 1 Workbook, Unit 6, Simple Harmonic Motion. Activity E, Equilibrium on an Incline. Please remember to pause or rewind the video as necessary. Let's begin. In this scenario, we have a cart of mass m is attached to a vertical spring of spring constant k, so that the spring stretches a distance x naught. When the cart is set into oscillatory motion on the vertical spring, the period of oscillation is t. The cart is then set on a smooth incline angled at theta above the horizontal and reattached to the same spring. Part A, using representations. The dot at the right represents the cart at rest on the incline. Draw a free body diagram showing and labeling the forces, not components, exerted on the block. Draw the relative lengths of all vectors to reflect the magnitudes of all the forces. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Okay, so here's what I like to do. I like to draw the forces on the actual mass itself and then transfer them to the dot. That way I know what I'm talking about. Here's what I mean. I know the forces involved would be mg, the weight, okay, normal force going out, spring force equals kx going up the plane, and then from there I've got my mg cosine of theta, which is exactly the same length as my normal force because they balance. And I've got this one here, which is mg sine of theta, and that is perfectly balancing Fs equals kx. Okay, now you're just simply going to transfer those three forces right here. Okay. Just like that. And then, as you can see, they're now drawn perfectly in lengths relative to each other. Okay, I just need to pull the normal force up a little bit like that. There we go. Part B, quantitative analysis. Derive an expression for the stretch of the spring L. Normally the stretch is X, okay, but the stretch of the spring is going to be L, while the cart is on the incline in terms of x naught, theta, and physical constants as necessary. Okay, let's begin. First thing we're going to do is we're going to set the sum of the forces on the cart equal to 0. Your net forces in the y direction are equal to 0. What that basically means, by the way, is forces up the incline equal forces down the incline. That's basically what that means. Therefore, the spring force and the gravitational force are equal in magnitude. So basically, we're talking about this one right here. Talking about the vertical one. Okay, so this force going up would be kx, and that equals the force going down, which is mg. So the expression for the spring constant can be written in terms of the weight of the cart and the original stretch. So let's solve for k. To do that, we're going to divide by x. So k is equal to mg over x. Now, it's mg over x naught, because this was kx naught. The sum of the forces equals 0 when it's at rest on the incline. So we just figured out okay, so now on the incline itself, again, sum of the forces equals 0, which means forces up the incline equal forces down the incline. . Therefore, the spring force going up spring force going up is going to equal to the component of the weight going down, which would be mg sine. Those two are going to balance each other. Which means kx equals mg sine. Okay, now I'm just going to rewrite it. KL equals mg sine. I'm replacing x with L, the length. And then what I'm going to do at this point, ladies and gentlemen, is I'm going to substitute for K. K is this value right here, because that value is going to remain constant. So I've got mg over x naught times L equals mg sine theta. The spring force is now equal to K times L, and we're substituting our value we found for K, which is mg over x naught. Okay, the mg's will cancel. Solve for L, multiply both sides by x naught. And L equals x naught sine of theta. Okay, now we can actually figure this out from the picture too. Part C, does your equation make physical sense for theta? Okay, so our equation is x naught times sine of theta equals our length. Here we go. Well, yeah, it does. Okay, here's why. If we let theta equals 0, that means x naught times the sine of 0. Now, sine of 0 is 0, which means L equals 0, okay? And what that means is there's going to be no stretch. There'll be no stretch of the spring. Okay, that would essentially, think about what that would be. That would just be a horizontal spring like this. There's no reason for it to stretch, right? Beyond its equilibrium position, it's just there. Now, what about, does your equation make sense for theta equals 90 degrees? Well, when L is x naught sine of 90, the sine of 90 is 1, which means L equals x naught. And that makes total sense, because if this is our original length, x naught, and we put a mass on the end of it, right, and this is our new length, L, well, actually, L would be this length here, right? That does make sense. So if the angle is 90 degrees, the ramp is now a vertical ramp, since the sine of 90 is now equal to 1, x naught equals L. Part D, how does the new period of oscillatory motion that the cart undergoes on the incline compare to the original period T when hanging vertically? Explain your reasoning. There is no difference. Okay, remember, period of oscillating mass is 2 pi times the square root of m over k. This does not change. And this doesn't change. Okay, so on the incline, you still have the same mass on the incline, you still have the same thickness of the spring on the incline, therefore the period is not going to change. Part E, the cart is pulled down so that it has been stretched a distance L past equilibrium. The cart is then released and oscillates. The equation for position of the graph as its function is sketched below. Sketch the following graphs for the cart as it oscillates on the incline, velocity time and acceleration time. Well, we're looking at x is equal to a cosine omega t. You can tell it's a cosine graph because we're starting at amplitude at time equals 0. Okay, that's a cosine graph. So now if we go from a cosine graph to a velocity graph, from a cosine to the next graph would be negative a omega sine omega t. And so we're graphing a cosine function, here we're graphing a negative sine function. Recall, a negative sine function looks like this. Cosine function looks like this. And then the acceleration function off of this would be, we're going from a negative sine function to a negative cosine function. All right, a negative cosine function starts at negative amplitude and goes up and down. They repeat as often because they have the same omega t, therefore the same period. Okay, so what do I need to be able to graph this? Well, I've got how many full periods? Let's see here. I've got 1, 2 and a half, and so I need to graph basically up until that point right there, which is 2 3/4 of a cycle. Not quite 3 full cycles. I'm going to graph 2 3/4 of a cycle here and here. All right, so what I'm going to do, 1 full cycle would be right here. So if this is 1 full cycle of a cosine graph, this is 1 full cycle of a negative sine graph. And then I'm going to go again. Then I'm going to go all the way down here. Okay, and I guess what would be easiest is if I just carried this graph over the top and made it 1, 2, 3 full cycles. Now you can see I've got 1, 2, 3 full cycles, so it matches. That's probably the easiest way to handle it. And then same thing with the acceleration graph. I'm graphing a negative cosine function, so I'm going to start down here. I got to return here, here, and here. So it would look like 1 cycle, 2 cycles, 3 cycles. AP Physics 1, Unit 6, Simple Harmonic Motion. Activity F, determining if motion is simple harmonic motion. Please remember to pause or rewind the video as necessary. Let's begin. In this scenario, a flexible metal plate is attached to one end of the table as shown in the diagram. Dominique connects a mass to the other end of the plate, displaces the mass a small distance, and observes that the mass vibrates up and down with a period that can be measured. She asks the following question, quote, I know the mass is oscillating, but does the mass exhibit simple harmonic motion? Dominique finds the following in a textbook. Not all oscillations, meaning periodic motions, qualify as simple harmonic motion. Simple harmonic motion is a special class of oscillatory motions. To qualify as simple harmonic motion, an object must meet the following requirements. 1, the graph must be sinusoidal. Okay, the graph must either be a sine wave or a cosine wave, right? Some sinusoidal graph. Number 2, the net force exerted on the object must be directly proportional but opposite to displacement. And thus, it must be, the acceleration must be directly proportional to but opposite to acceleration. And then finally, the period of motion must be independent of amplitude. Okay, no matter how big you stretch it, it's going to have the same motion in the same repeating period. Dominique wishes to determine experimentally whether the mass exhibits true simple harmonic motion. Note, the statements above are equivalent. If one is true, they all are true. Experimental design. Dominique has access to the materials below. Mark the space next to the piece of equipment that she would need in order to determine whether or not the plates exhibit simple harmonic motion. Okay, so what we're going to do is we're going to test them one at a time. The first one that we're testing is the idea that it makes the graph of a sine wave. By the way, It's best to figure out the problem first, figure out a solution to your problem first, then write about it in terms of a procedure, right? Do this first, then this, then this. And then once you come up with your procedure, then check off the equipment last. Save that step for last. Because if you check off something and you don't use it in your description, you get marked off for that point. And that's a really easy point to check off the equipment use. So always do that last. All right, so let's take a look at the first one. How do we experiment to see if we get a sinusoidal function? Well, simple. We're going to put, you have your, here's your end of your table. Here's your vibrating mass. And you're going to set it into oscillatory motion, but you're going to place a motion detector right below it. And when this thing goes away and towards this, what you're going to see is you're going to record that position for at least 3 periods. Okay? 3 is enough to get good sufficient data that repeats, but if you can do more, then do more. The next piece of criteria is that the net force is directly proportional to displacement, but opposite in direction. Well, we can hold up a meter stick, okay? Hold up a meter stick to the end of each plate. On each trial, use a balance to determine different amounts of mass, M, and then attach it to the plate. Record the stretch against the meter stick. So basically, as soon as here's the edge of the table, like this. If we put a mass at the end of it, it's going to bend down a little bit. This was the distance L that it's bending down. So we're recording that. Okay, and then finally, how do we test the third one, which is the period is independent of amplitude? Okay, very simple. You're going to put your meter stick to the end of the table. You're going to make the plate oscillate with different amplitudes, 1 centimeter, 2 centimeters, 3 centimeters, etc. You're going to time for 10 cycles, divide by 10 to get the period for each trial. In other words, we're going to pull it back a different amount every time and see what the result comes out to look like. So using that, we can see we used a motion detector. So let's go ahead and click that. We used a meter stick. So click that. Okay, we also, let me see what else we also used a balance. Okay, now keep in mind a spring scale held up vertical will also allow you to determine mass too, so either one of those is fine. Use a stopwatch to time for 10 cycles. So make sure you write about it first, right? And then go back and check off, right, the appropriate ones. Part C, explain how the data can be represented to answer Dominique's question about the motion about the motion of the fixed object to the metal plate. Give an example of the representation that would indicate the object exhibits simple harmonic motion. Well, you have a motion detector. If the graph is sinusoidal, right, it's simple harmonic motion. If it's not, then it isn't. Okay, here, net force equals MA, or rather, net force equals KX. Okay, and if we plot, keeping in mind that the force pulling down on it is mg over kx. Okay, x is L, so mg equals KL. Divide both sides by that, and we get mg over L equals K. This is my rise. So graph mg versus L. This is my run. That means K would be my slope, right? Okay, and then finally, graph the period versus the amplitude. If we get something like this with horizontal data, that's telling you that amplitude does not affect period. AP Physics 1, Unit 6, Simple Harmonic Motion. Activity G, period and amplitude for simple harmonic motion. Please remember to pause or rewind the video as necessary. Let's begin. In this scenario, consider a class of physics students in a 3-story schoolroom with a high ceiling. In other words, the ceiling is high enough to be the ceiling of the 3rd floor. That's a very tall classroom. The teacher connects a long rope to the ceiling. The free end of the rope is connected to a heavy ball that almost touches the floor when the rope is vertical, creating a very large-scale pendulum where the ball travels almost completely in the horizontal direction. That means the pendulum's just moving forward, not in a circle in any way. The teacher pulls the heavy ball a small distance to the side and releases it so that it oscillates with a certain period, amplitude, and average speed. The teacher then repeats the demonstration but releases the ball from greater displacement than before. The teacher asks students to think about how the period, amplitude, and average speed will change for this greater displacement. Carlos and Angela agree that the amplitude will be greater but disagree on other points. They reason as follows. Angela says, the period will be greater because the distance of the ball must travel in one cycle, depends on the amplitude. The greater the amplitude means a greater distance, which means it takes a longer time to complete one cycle. Carlos says the period should be shorter because the ball will have a greater average speed as it cycles. Greater average speed would mean that it takes less time to complete a full cycle. Part A, quantitative analysis. Suppose A represents amplitude and the distance traveled by the ball from equilibrium to one endpoint of its oscillation, and T represents the period of oscillation. Write an equation for V average, the average speed, in terms of amplitude and period of the ball as it oscillates. Okay, average speed is total distance divided by total time. The total distance of one cycle is 4 times the amplitude. Let's see if it makes sense of that. So here is the equilibrium right here. If we pull it back to this point here, it's going to go, this whole distance here is the amplitude from here to here. So it's going to swing 1 amplitude, then over to the other side, that's 2, then 3 coming back, and then 4. So there are 4 times the amplitude divided by the time. Total distance divided by total time. Explain how this equation supports Angela's reasoning. Okay, well, Angela is saying that a greater amplitude means a greater distance. Okay, if the average speed is independent of A, then Angela is correct because larger amplitude in the numerator means a longer period. Explain how this equation could support Carlos's reasoning. If Carlos is correct, the average speed will be much larger in the denominator, and then the period T will be shorter. Right? Larger average speed, right? Lower period. Part B. Carlos is correct that a greater amplitude of oscillation will result in a greater average speed. Explain why this is the case, reasoning in terms of forces exerted on the ball as it oscillates. At greater angles, there is a greater component of force tangent to the path of the ball. See, the greater force results in a greater maximum speed and thus a greater average speed. Explain this again, but in terms of mechanical energy of the ball-earth system. At greater angles, the ball is lifted to a higher height. This gives the ball Earth system more gravitational potential energy, which means it'll transform into more kinetic energy in the fall. Part C. Give one correct prediction about whether the period increases, decreases, or remains the same as amplitude. As the amplitude increases, assuming the pendulum undergoes small angle oscillation. So the period of a mass spring oscillator, right, is 2 pi times the square root of m over k. Well, nowhere in here is there a variable for amplitude, so making a bigger amplitude is not going to change the period of oscillation, so it is going to remain the same. Okay, if the angle stays the same, the pendulum will undergo simple harmonic motion, 3 period t, and the period t, that should be the period t has no dependence on amplitude. Okay, using the equation, period equals 4 times the amplitude over the average speed. The average speed of the ball and the total distance would increase because both are directly proportional to amplitude. They would both divide out and thus would have the same period. So this is, in other words, that increases and that increases by the same amount. AP Physics 1, Unit 6, Simple Harmonic Motion. Activity H, Period and Mass Relationship for Mass Spring Systems. Please remember to pause or rewind the video as necessary. Let's begin. In this scenario, Carlos and Dominique hang a spring with an unknown spring constant from a ceiling. The students connect objects of varying different amounts of masses m to the spring and measure the oscillation t for each object. The data is shown to the right. Note that the square of each period is also calculated. Part A. The students did not take care to ensure that the objects oscillated with the same amplitude. Their teacher informs them this oversight will not invalidate their experimental results. Why? Well, again, if you recall, this is a simple harmonic motion of a mass spring oscillator. And that equation that relates those concepts is the 2 pi times the square root of m over k. So in other words, mass affects the period of a mass spring oscillator. The stiffness of the spring constant affects it, but amplitude has no effect on it, right? Period is independent of amplitude. Okay, now we're going to grid t squared versus the mass, okay? Why is that? Well, start with the equation. T squared is, T is equal to 2 pi times the square root of m over k. Okay, I want you to square both sides and rewrite. We get t squared equals 4 pi squared m over k. Here, t is a variable, mass is a variable. I want to bring my variables together and write them as dependent over independent. Period is the dependent variable. Actually, t squared is the dependent variable, but period is the dependent variable, and mass is the independent variable. So I need to divide by mass. If I do that, I get t squared over the mass equals 4 pi squared over k. Well, t squared, there's your rise. Mass, that's your run. Rise over run is equal to your slope. Okay, so that means that's equal to your slope. So how do we solve for the spring constant if we need to? We're going to switch out those two, and k is going to be 4 pi squared divided by your slope. Okay, let's go ahead and graph this. Well, first let's scale each axis. We got t squared, second squared on this side. You've got mass in kilograms on this side. Okay, so scaling your t squareds, your largest t squared is 4.24. So I'm going to go 1, 2, 3, 4, 5. My largest mass is 5.86, so I'm going to go from 1 to 6. So 0, 1, 2, 3, 4, 5, and 6. Okay. Then we have, let's plot them one at a time. So first I'm going to go over 1.15 and up 0.61. So this is about 1.33. That's about 1.67. 1.15 would be about halfway right there. So, and then go up about 0.6. So 0.2, 0.4, 0.6, 0.8. So the first point is roughly about there. Okay, second one, we're going over 2.3 and up 1.46. 2.3 is about 2 1/3 right there. 1.46, well, 1.2, 1.4, 1.6, so 1.46, a little bit higher. About right there. Okay, then we're going over 3.5, up 2.6. 3.5 is right here, up 2.6 would be exactly right there. Okay, and then we're going over 4 3/4, over 4.8, and we're going up 3.5. So we're going over that amount and then up 4 1/4. So 4.2, a little over 4.2, that would put it about right there. Okay, and finally, we're going to go over 5.9 and up 4 1/4. Oh, I'm sorry, I did it backwards. I wanted to go 3.5. So let me get that back down. That point belongs down here at 3.5. There we go. The last point is at 4 1/4. So 5.89, it's over here. 4.2, it would be roughly about there. Okay, so you got your points. We need a best fit line. Let's go ahead and do that. Okay, now I'm looking for two convenient points so I can find my slope. I really like that point right there where it crosses the grid, and perhaps maybe that point right there. So make your slope triangle from one to the next. Okay, and my remember, every box is 0.2, right? So 0.2, 0.4, 0.6, 0.8. My rise is 0.8. My run is going 3 boxes over, and 3 boxes is 1. So my run is 1. Okay, so my slope is equal to 0.8 over 1, which is just 0.8. Okay, we're going to come back to the use of that slope shortly. So now it says an unknown object is hung on the spring, has a period of oscillation of 1.47 seconds. Use your best fit line to calculate the mass of the object. So here's basically what you do. You take your T10 to get your period, right? That right there is your period. You then square your period. Why? Because that's on the y-axis of your graph. You then go to your best fit line and then go down to your mass. You read off your mass. Okay, so let's take our calculators out. Okay, go ahead and square 1.47. Okay, now we get about 2.16. T squared is about 2.16. So I'm going to go over to 2.16. That's about 2.2 and a half. 2.2 is here, so 2.16 is about right there. You're going to go over to the graph. You can see it intersects right there, and then go straight down. okay, and that's approximately a 3 kilogram mass. Okay, so again, to summarize, a period of 1.40 seconds corresponds to a t squared of 2.16 seconds squared. Reading from the best fit line, 2.16 seconds squared corresponds down to a mass of approximately 3 kilograms. Okay. Using your best fit line, not merely a single data point, calculate the spring constant. Okay, explain how you did that. Well, basically, here's what we did. I'm just gonna copy and paste this because this is exactly what we did. Okay, and then using that, we're just gonna find the spring constant from there. So K is equal to 4 pi squared is approximately 39.5. And we're going to take that and put that over the slope, which I got a slope of approximately 0.8. So 39.5 divided by 0.8 is approximately a little over 49 newtons per meter. Okay, you should get somewhere basically around 50. Okay, some cases you might get up to 55, but it's going to be an approximate range of acceptable answers. I got 49 for mine. Part E. Suppose Carlos and Dominique also made a graph of t squared versus mass. However, the graph they made has a best fit line slightly steeper. In other words, what is a steeper slope going to give you? Well, use this right here. Steeper slope means K is going to be smaller. Steeper slope leads to a smaller spring constant K. How would this affect their value for the mass, okay, of a period 1.47 compared to your answer in part C? Well, if you had a steeper slope, so I'm going to draw another line here. We'll do gray. Say our slope was a bit steeper, like that. You can see 2.16 would now mean somewhere over here, which corresponds to a lower mass. Okay, and that should make sense because if you go to your equation, T is equal to the square root of 2 pi m over K. So if the period is the same, okay, period's the same, but the spring constant is now less. Okay, so what I'm going to do is I'm going to solve this equation. So we get T squared equals 4 pi squared m over K. And I'm going to actually solve this for m, for mass. So to solve for mass, I've got kt squared over 4 pi squared. Now 4 pi squared is a constant. K got smaller. T got the same. So the only thing that's changing is really this. And if the spring constant got smaller, the mass got less. And you can see that from the graph, the gray arrow right there. Steeper slope would lead to a smaller value of mass.